Good morning everybody. Today we are starting with the first topic of the syllabus, that is chemical kinetics. For every reaction, the two features are very important. The first is whether the reaction can occur and the second is speed of reaction. To study these two features, out of this first, whether the reaction can occur, thermodynamics can be used to study the reaction. Whether the reaction can occur or not, that can be studied with thermodynamics, while the speed of reaction is studied with the chemical kinetics. With the thermodynamics, we can only predict whether the reaction can occur or not. From the value of delta G, if it is less than 0, therefore the reaction is spontaneous, while if it is greater than 0, then it is a non-spontaneous. But with the help of thermodynamics, we cannot predict the speed of the reaction. For that, we need chemical kinetics. Therefore, chemical kinetics, this is a branch of physical chemistry which involves deciding the rate of the reaction and the mechanism by which they take place. So, this is a branch of physical chemistry which studies specifically the rates of the reaction. In the chemical kinetics, some reactions are very fast while some reactions are very slow. The reactions which are very fast or very slow, their rates cannot be determined with the help of chemical kinetics. The reactions with a moderate speed, their speed or the rate can be decided or determined with the help of chemical kinetics. Various methods are used to decide the rates of the reaction. There are the different terms which are present in the chemical kinetics. First term, that is the rate of a reaction. The rate of reaction is basically, it is defined as the decrease in the concentration of the reactants or increase in the concentration of a product during the reaction with a time is called as the rate of the reaction. And this rate of reaction is expressed as, see, this is the simple first reaction we are taking. The reactant A converts into the product P. The rate is expressed as minus dA by dt with respect to the reactant, or it may be expressed in terms of product as dP by dt. Here the difference, the derivative of the concentration of the time is taken. Over a small time interval, the change in the concentration is measured, and this is how the rate is expressed. Here you can see that where the reactant is taken, or with the respect to the reactant rate is expressed, a negative sign is given. The negative sign indicates that the concentration of the reactant decreases, and as well as the rate of the reaction also decreases with the time. While here with respect to the product, the rate is expressed. Here no negative sign is there, which shows that the rate of formation of the product increases with the time, or even the concentration of the product also increases with the time. Here is the graph. The graph is concentration versus time, which shows, here this is the graph for the reactant while this is the graph for the product. From the graph we can easily see that the rate of the reaction or the concentration of the reactant decreases with the time, while the concentration of the product increases with the time. The another example here, twice of A plus B gives the product. Here how the rate is expressed? Here the coefficient, the stoichiometric coefficient of the reactant A is taken as minus half of dA by dt, or with the respect of B it is expressed as minus dB by dt, or with respect to the product the rate is expressed as dP by dt. This is the general example. Small a, small b, small c and d. These are the coefficients, stoichiometric coefficient in a balanced reaction. This is how the rate is expressed therefore for this reaction. It can be expressed as minus 1 upon a dA by dt is equal to, or minus 1 upon b dB by dt, or 1 upon c dC by dt, or 1 upon d dP by dt. These are the concentration terms. The square bracket, these are expressing the concentration terms. So this is how the rates of the reactions are expressed. Now the second term of the kinetics, that is the rate law. Now according to the mass of the rate of any reaction is directly proportional to the concentration of the reactant, and depending on that the rate law is determined. The rate law is defined as the mathematical relation between the rate of the reaction and the concentration of the reactant is called as the rate law for that reaction. Now, for example, here, this reaction we had seen. So, therefore, rate is expressed as the rate is equal to minus dA by dt, which is equal to K into concentration of A. So, this is the rate law for this reaction. Rate is equal to K into concentration of A, where this small k, this is called as the rate constant, or it is also called as specific reaction rate. If we consider this concentration, the concentration of A as a unity, if we consider the concentration of A as a unity, therefore this equation becomes R is equal to, this is unity, therefore rate is equal to K. That means the rate constant K is defined as, it is nothing but the rate of reaction when all the reactants are at their unit concentration, or the reactant concentrations are at a unity. So this is nothing but the rate constant, or it is also called as specific reaction rate. Now for this reaction, what will be the rate law? The rate law will be rate is equal to K into concentration of A raised to 2 into concentration of B. Now the rate laws, these are determined experimentally. From the balanced chemical reaction, you cannot write the rate law. These exponents or these concentration terms which are appearing in the rate law, their exact change in concentration is determined experimentally, and then the rate law is defined. Let's see some example. In this reaction, the rate law is, the rate is equal to, rate of reaction is equal to K into concentration of Hi raised to 2. Here, this is the reaction, and here the concentration of Hi raised to 2. That means here this is mole being involved in the reaction, which undergoes the change in concentration. The another thing, in the rate law, the concentration terms of reactant which are appearing, those are the only reactant which undergoes change in the concentration. Only those reactants appear in the rate law. For this, we see one example. Now, in this example, the rate law is K into concentration of this is the rate law for this reaction. Now see here, these are the two reactants. But in the rate law, the concentration term of only this, that means the ester, that is only appearing. This means that the water, which is actually a reactant, which is participating, but the concentration of water is so large that the change in its concentration is very negligible, and hence therefore the water concentration term does not appear in the rate law. Therefore these rate laws are experimentally determined, and in the rate law only the reactant concentration terms only appear whose concentration changes during the time. So this is how the rate laws are. The next term is order. Order is also an experimental quantity which is determined. Actually, it is determined from the rate law. The order is nothing but the sum of the exponents to which the concentration of the reactant terms are raised, that is called as the order. That means, see here, in this example, the rate is equal to K into A. The exponents here is a 2 and here it is 1. Therefore, the order of this reaction will be, the order of this reaction will be 2 plus 1, that is 3. In this example, twice of A plus B gives the product. The rate is equal to here K into concentration of A raised to 2 while into the concentration of B raised to only 1. So order of this reaction here, the summation of these exponents, that is 2 plus 1, 3. Another example we can see, acetaldehyde, which is methane plus carbon monoxide. In this example, the rate law here is rate is equal to K into concentration of acetaldehyde raised to 3 by 2. That means here how much is the order? That is 3 by 2. So order can be, it can be positive integer, it can be fractional, as well as it can be 0 also. See, in this reaction, here the rate is equal to just K. None of these two concentration appear in the rate law. With respect to these two reactants, the order of this reaction is a 0. That means for this reaction, in this reaction, the rate of this reaction does not depend on either the concentration of H2 or Cl2. Therefore, this order is an experimentally determined quantity and it can be a positive integer, 0 as well as a fraction. And the last term in the kinetics, that is the molecularity. Now, molecularity is completely a theoretical concept. We know that some reactions can take place in the many states. So, every state is called as the elementary reaction, and the molecularity is the number of molecules involved in an elementary reaction. म्हणजे एखादी balanced reaction असेल, in a stoichiometrically balanced reaction, elementary reaction, the number of reactant molecules involved in it is called as the molecularity of a reaction. We had seen the example of a hydrolysis of a ester. In this example, we know that order of this reaction, we had seen the rate law, that is rate is equal to K into concentration of methyl acetate. Here the order is 1. But if we see the molecularity, how many molecules are involved in the chemical reaction? 2 molecules are involved, hence the molecularity 2. So this is completely a theoretical concept. The number of molecules, reactant molecules which are involved in an elementary reaction is called as the molecularity of a reaction. If only one molecule is involved, therefore it is called as the unimolecular. If 2 reactant molecules are involved, bimolecular, and if 3, trimolecular. So this is how the molecularity is. The order and the molecularity, these two are the different concepts. We can differ in them. The order is sum of the exponents of the concentration terms which are raised in a rate law, while the molecularity is only the number of the molecules which are involved in an elementary reaction. Order is experimental quantity, while molecularity is a theoretical quantity. Again, one point of difference is order changes with the reaction conditions like concentration, pressure or the temperature, while the molecularity does not changes with the reaction condition. The order can be 0, fractional or a positive integer, So these are the point of differences in between these two. Next time we will see the different factors affects the rate of reaction.